Okay, our final subtopic for this topic, relativity. Now, relativity, it can be a really, really confusing thing. It can be a really, really interesting and intriguing thing. It's one of those things, though, sometimes the more you know, the more questions you have, in a sense, the more the confusing that it can get. What I'm really going to try and do here is just give you the essentials, the, the, the basic knowledge as simply as I can for what you need to know for this course. If you have more interest in it and you want to have a look into it deeper, that's great, and I encourage that. There is, a lot better stuff out there that goes into a lot more detail, but when I watch that stuff, it raises even more questions, and sometimes that makes me even more confused. So I am going to try and keep it fairly simple for you. However, by all means, if you're interested into this, dig deeper, but just be prepared to have your mind expanded, or maybe toyed with a little bit if you do. Let's get into it. Okay, so if you haven't already, please watch this Special Relativity Crash Course Physics number 42 episode. I've got the link here, but I've also put it up on Teams to have a look there if you're following in my classroom. I think this video basically hits just the right mark in terms of the level that we need to understand relativity at for this course. We do one additional bit that's not covered in the video on momentum, but that's the last thing we do, and I think that's relatively straightforward. So let's get into what we need to know. Some measured quantities of objects travelling at very high speeds cannot be explained by Newtonian physics. By Newtonian physics, we mean the equations of motion, Newton's laws of motion that we currently understand them, like Newton's first, second and third law, and all those equations for objects undergo constant acceleration and all that sort of thing. They basically break down as we approach the speed of light. Einstein's theory of relativity predicts significantly different results to those of Newtonian physics for velocities approaching the speed of light. So as we get near the speed of light, we can't use Newtonian physics, Newton's laws of motion. We need to use Einstein's theory of special relativity. And basically the predictions and the results that you get from those two models can become quite different. At normal speeds, well below the speed of light, there's no significant difference between the values that you get. And honestly, you could use Newtonian physics to just about travel to the moon. Even at the speeds involved in those sort of things, the effects of relativity are going to be very, very, very small. So let's get into the theory of special relativity. And it's based on two postulates. So these are sort of two underlying principles to the theory of relativity. And the first one is the speed of light in a vacuum is an absolute constant. Well, what do we mean by that? Well, if you are on a spaceship and you're travelling at half the speed of light, so c is just the speed of light. If you're travelling at half the speed of light and you shined a laser forward, that light will not travel at, you might think, if you're travelling at half the speed of light and you shine a laser forward, that travels at the speed of light, so that will basically travel at 1.5 c, 1.5 times the speed of light. But no, that doesn't happen. That is wrong. If you shine a laser light on that spaceship, it will still travel at the speed of light c, which is basically 3 times 10 to the 8 metres per second. And it doesn't matter whether this spaceship is stationary and it shines the laser, or if it's travelling at 100 kilometres an hour and it shines the laser, or if it's travelling at, say, the speed of sound, 330 metres per second, or if it's travelling at half the speed of light. The speed of the light that's coming off this laser will still be travelling at 3 times 10 to the 8 metres per second. So that speed of light is constant. It doesn't matter how fast the object that's shining the light is moving at. The next postulate is that the laws of physics are the same in all inertial frames, in all inertial reference frames. So by that we mean inertial, we basically mean not accelerating. So Newton's first law is about inertia. That says that a body moving at constant velocity. So the idea of constant velocity, not accelerating, is what we mean by inertial. So the laws of physics are the same as long as, it doesn't matter how fast or slow the reference frame is moving, or as long as it's not accelerating, all those laws of physics that we've talked about are the same in each inertial frame. So this leads to this idea, and you would have seen this explored in the special relativity crash course video. If you've done the right thing, then watch that. Is that, at the moment we have this idea that basically distance is equal to speed multiplied by time. So yeah, if we're travelling somewhere at 100 kilometres an hour for 2 hours, we'd travel 200 kilometres. So that, that's a basic sort of relationship. I think we're all comfortable with that. But what we're saying, because of that first postulate, is if we're dealing with light here, if this is constant, so the speed of light is constant, an absolute constant, it doesn't matter about how fast or slow the object is moving that the light's being emitted from, that if the speed is constant, that must mean that both the distance and the time, or at least one of these, must be not constant. So what that is saying is, in this case, for the speed to be constant, the rate that objects experience time must be not constant. So the rate that time passes is not the same for every object. Or the distance between two objects, or the distance covered, is not constant. So, it's got to be, for the speed of light to be constant, one or both of these, distance and time, need to be not constant. And in reality, it's actually both the distance and time are not constant. And that leads to the principle of time dilation and length contraction, which is what we are going to look at in the upcoming slides. Let's keep moving. So time dilation. The most important thing to remember is at relativistic speeds, time intervals are dilated. Let's dig into that a little bit more. What we mean by relativistic speeds is we mean at very high speeds, where we're getting near the speed of light. So relativistic speeds, very high speeds. Time intervals are dilated. So dilated is just another word for increased, or if we're thinking about time travels slower, or things take longer. Probably you should use inverted commas for those things, but they're just different ways to think about it. So, if I was to sort of summarise that even quicker, when we're dealing with a moving frame of reference, in that moving frame of reference, the time will be longer, or time will travel slower. So moving equals slower or longer or greater time. Whichever one, just move that out of the way, whichever term fits best with you, but that's just the best way to remember it. So now let's talk about, as it's just popped up on my screen because of the way I'm editing, let's talk about how much slower time travels in a moving frame of reference. And the way that we work that out is using the Lorentz factor. And the Lorentz factor is calculated according to the formula we have here. So we use the symbol from the Greek alphabet here, gamma, for Lorentz factor. And it's equal to 1 divide the square root of 1 minus v squared over c squared. So if you think about this, if we're travelling at low speeds, which is what we do in our normal everyday lives, v will be much, much smaller than c, the speed of light. So this number here will be almost equal to 0. Therefore, 1 minus 0 is effectively equal to 1. Square root of 1 is equal to 1. So basically, at sort of normal, inverted commas, at normal speeds, that gamma will be approximately equal to 1. So the time that the length of time, well, the rate at which time passes in the stationary phase of reference will be the same as what it is in the moving frame of reference. We'll get to that formula in a sec. But at the relativistic speeds, at the high speeds, then gamma will be greater than 1. So if gamma is greater than 1, that means that the time as observed from the stationary reference frame will be greater than the time observed from the moving reference frame. And that's because I've sort of jumped ahead a little bit there. The relationship between the time as it's experienced from a stationary frame of reference, i.e. the person standing on the platform watching the train go past, will be greater, because this number here will be greater than 1, than the time experienced by the person in the moving reference frame, i.e. the person on the train moving at near the speed of light, or at any speed, but it's only really significant as you get to speeds approaching the speed of light. So, I'm not sure how clearly I did that, but I'm sort of happy. I'm happy enough, I think, that I'm not going to re-record it. All the rest of the stuff here is basically almost an application of this to do with subatomic particles and why they can be observed and not observed. This thing's called muons. I'm going to cover that at the end. I'm going to do an example problem that really covers how we do all these things, calculate, solve problems. So the rest of this stuff here will come at the end. But hopefully I've explained to you the concept of time dilation in not too complex terms. Let's move on now and look at length contraction. So, an object moving at relativistic speeds appears shorter. We know what relativistic speeds is now, very high speeds. I don't think I need to explain shorter. I think most of us are very comfortable with the term shorter and longer, whereas dilation was not such a clear term. So, mathematically, how do we say this? Well, this formula here gives the relationship between the length in a moving frame and the length in a stationary reference frame. So the length, gamma here, we just talked about on the previous slide, at relativistic speeds, gamma will be greater than 1. So if this number here is greater than 1, then L will be less than L naught. So what this basically means is that if you are standing on the platform and the train is moving past you really, really, really fast, then the length that you will see will appear to be shorter than the actual length of the train. So if the train was 100 metres long and gamma was say 1.1, then the train's only going to appear to be roughly 1 divided by 1.1. It's going to be roughly 90 metres long. The train will appear shorter. So always remember that an object moving at relativistic speeds appears shorter if you're observing it from a stationary frame of reference. I'll pause there and move on before I say too much and confuse the matter even more. I think that is in essence all that you need to know for this course. So let's finally consider momentum and mass at relativistic speeds. Now, I must admit, when I learnt this at uni, at least my memory of it, was I learnt that as an object approaches the speed of light, so relativistic speeds, its mass increases, and then effectively, if any object with mass could reach the speed of light, at that point it would have an infinite mass. Therefore, that's just not possible. So, and obviously it's not possible to apply enough force to accelerate an object of infinite mass, so there's no way that any object of mass could reach the speed of light. Now, in this curriculum, we don't use mass specifically, we use momentum, but it has the same meaning. So, as an object increases in velocity, basically, as we reach these high relativistic speeds, gamma starts to approach, gamma starts to approach a very, very large number. So gamma becomes larger and larger and larger as we reach high speeds. So that basically means as gamma becomes larger, the momentum becomes larger. So an object travelling theoretically at the speed of light would effectively have infinite momentum. Now, if we wanted to have infinite momentum, if we think about the formula that we learned earlier, that basically, force equals the change in momentum divided by time, or the change in momentum will be equal to force multiplied by time, you can see we would need to basically have an infinite force to accelerate, to give an object infinite momentum. So, that's basically not possible. So that's why any object with large mass, any object with mass as it approaches the speed of light would have very, very, very large momentum, which would therefore require very, very large force. And that would be tending towards having infinite momentum, which would require infinite force, which is basically just not possible. So, hopefully that explains this last bit here, why masses moving at relativistic speeds are unable to reach the speed of light, because they would have infinite momentum, which would require infinite force to accelerate them there, which is not possible. So that covers the three main relativistic effects, if you like, that we need to cover: time dilation, length contraction, and momentum and mass. I talked about at least how I learnt and experienced that in terms of mass and the way I think of it, but I think it's equally valid to think of that in momentum and not that much more difficult. What I will do in the final slide is do an example calculation which uses this information that I have just described. Let's get on with it. So, muons are a type of lepton. A particular muon travels at a constant speed of 0.990 c, so 0.990 the speed of light. Show the Lorentz factor of this muon is 7.09. So firstly, we have to convert the speed into metres per second, so that the velocity is equal to 0.990 times 3.00 times 10 to the 8, which is equal to 2.97 times 10 to the 8. Then we put that into our meters per second, let's be really correct. Then we put that into our Lorentz formula equation, which says that Lorentz factor equals 1 on the square root of 1 minus v squared on c squared, which is equal to, we'll show our substitution to be really thorough here, 1 minus 2.97 times 10 to the 8th squared over 3.00 times 10 to the 8th squared, and we put that all into the calculator, and that will spit out an answer of 7.09 as required in the question. Now, that was the thorough way to do that. Because this here, let's use this here, because this here is a ratio, I equally could have said 0.990 squared over 1 squared, and 1 squared is obviously equal to 1. So didn't mean to do that, hang on. I could probably have equally just ignored the 1 there and just put 1 minus 0.990 squared into that formula, and I still would have got the same answer that I got here, 7.088, which rounds off to 7.09 to 3 significant figures. So you can use either approach there. Doing the shortcut way is a little bit simpler if you're given the speed of light in terms of c, but if in doubt, do it the long-winded way and don't worry about risking making another mistake. So part B and the first part of that, it can get a little bit confusing here, but hopefully not too bad. The muon has a lifetime of 2.2 microseconds, so that's times 10 to the minus 6 seconds. As I quickly check, those conversions are on your formula sheet. For micro, it says it's 10 to the minus 6. So the muon has a lifetime of 2.20 microseconds in its own frame of reference before it decays. Calculate the distance travelled by the muon in its own frame of reference before it decays. So remember, the laws of physics in all inertial frames of reference are the same. So here we're dealing with a time in its own frame of reference. We want to know how far it travelled in its own frame of reference. So we just use the normal laws of physics, which would say that basically you could either say displacement, it says distance. Whether you use displacement here or distance doesn't really matter. I've changed my mind. I'm going to go with, distance equals the speed multiplied by time. So that is going to equal 2.97 times 10. So you did need to work that out in meters per second for this question, even if you didn't for the previous question, times by 2.20 times 10 to the minus 6 equals 653 meters. I think we're at 3 significant figures everywhere. Yeah, so 653 meters. So because we're in the same frame of reference, we don't need to bring in the Lorentz factor and do those corrections. So calculate the distance travelled by the muon in the frame of reference of a stationary observer before it decays. And so this is where it can get a bit confusing. The temptation is to go, this is about length contraction. So L in the stationary is equal to L in the moving divided by gamma, and to plug into that 653 divide 7.09, and you get an answer of, I don't know, something like about 100 meters very roughly. But that is wrong. Don't do that. we're not dealing here with the length of a muon. This is about the length of an object to an observer. We're dealing with the distance something travels. So when we're dealing with the distance something travels, we need to think about both its velocity and its time. So it's better here that we need to think about the time dilation, and we need to go, well, the time to an observer on Earth will equal the Lorentz factor times by the time to the moving observer, and in this case that is the muon. So that is equal, oops, just lost my pen, that's equal to 7.09 times by 2.2 times 10 to the minus 6 seconds, which is equal to what have we here, 1.5, what have we got, three significant figures? Yeah, 1.56 times 10 to the minus 5 seconds. So to an observer, a stationary observer on Earth, the 2.2 microsecond lifetime of the muon would appear to be 1.56 times 10 to the minus 5 seconds. So how far would the muon travel in that time? Well, we would just do distance equals velocity or speed times time, and we would get that's equal to 2.97 times 10 to the 8th times by 1.56 times 10 to the minus 5, and that is equal to 4,630, let's round off to three significant figures, metres. So that is, I know, a little bit confusing. There is a way you can do it with the length contraction formula, but it's a little bit more conceptually difficult to think of. So I think when you're dealing with muons, remember you're not dealing with the length of the muon, you're dealing with how far it travels. So you need to know how long it travelled for and at what speed it travelled to work out how far the muon would travel. And this experiment was really, really important because essentially we regularly observe muons at the surface of the Earth. Now, if the muon basically has this short lifetime, most muons are formed in the upper atmosphere about 10 kilometres above the surface of the Earth from radiation from the sun striking the upper atmosphere. If those muons only travelled 653 metres, we would expect very, very few muons to be able to travel to the surface of the Earth, because it's obviously got to travel a lot more than 653 metres to travel that 10 kilometres through the atmosphere. However, we do see significant amounts of muons at the surface of the Earth, and that is because of this time dilation and the relativistic effects, that they travel much, much further than you would expect. There is, a more complex way to explain that, but I do not want to even try that. I just think if you're dealing with the distance covered, don't use the length contraction formula, use time and then distance equals speed times time. That is the best suggestion I can give you to navigate these questions. Okay, that's it for relativity, and that is it for the motion and relativity topic. If you like this video, click like. If you want to see more of this action, click subscribe. Cheers.